Fernando Brandao, and he'll speak on information-theoretic techniques in many-body physics. Thank you.
Thanks, Richard. So, good afternoon. Thanks the organizers for the invitation to talk here. It's a pleasure. I'm going to talk about a connection between many-body physics and, on one hand, and quantum information theory on the other hand. And I will talk about several things, mostly joint work with Aaron Harrow and Michał Horodecki, like different papers. So just for motivation, the motivation comes from trying to understand quantum many-body systems. And here, so please let me know if you have any questions at any time, or if I'm going too fast or too slowly, just interrupt me. So it'll be interesting in what we call quantum Hamiltonians, and this is just some you can have on a line a bunch of spins, so d-dimensional spins, for example, and we imagine that they are interacting somehow, and that they have, for example, local interaction. So here, this spin interacts with this one, with this interaction term. So you can think of this Hamiltonian as just a sum from 1 to L of local terms, where these local terms, they have the property that they only act non-trivially on a few of the spins. For example, here 2 of them. Or they could act on 3 of them and so on. But we have this kind of Hamiltonians where we just have a sum of things that act locally. And so because physics is usually local, that's why we're interested in this kind of models. And given some particular physical system, we have a Hamiltonian describe this physical system, and we like to understand properties about the system, right? So there are several properties that we like to compute or to estimate. For example, the minimum energy of the model is really just the minimum eigenvalue of this Hamiltonian, right? This is what we will be mostly concerned here, but you could also be interested in computing maybe correlation functions either at 0 temperature or finite temperature, or maybe some dynamical properties and so on. So one way to look at this problem, this quantum Hamiltonian problems, is as some generalization of constraint satisfaction problems in computer science. And I won't need this so much, but let me just show you how we make this connection, just so that if you're not so used to Hamiltonians, you see that they are a natural object. So imagine that we have a constraint satisfaction problem of area Tk, right? So this just means that we have a bunch of variables, x1 to xn, and each one have an alphabet, just ranges over some finite set sigma, is the alphabet. So for example, if they were binary variables, it would just be 0 or 1. And then we have these variables, and we have some constraints on the variables, given by Cj. So this Cj is just a function from k-fold copies of this alphabet into 0 or 1, right? So if the constraint is satisfied, then they would say it gives 0. If it's not, when it gives 1. Right, so for particular values of the variables, it gives either 0 or 1. And now we would like to find some assignment for these variables, just put values on these variables, which satisfy as many constraints as possible. So assignment is just a function, right, from this n variables to, for each one of these variables, we just put one of the possible values of the alphabet. For example, if it's binary variable, it's just here 1, 0, 0, 1, and so on. And how many constraints are being violated, we call this unsat, is just this, right? We minimize over all assignments the sum of the constraints. So this, if you like physics, you just kind of think this as a classical Hamiltonian, right? And this is just minimizing the energy of this classical Hamiltonian. And what we want to do in the quantum case is just some natural generalization, right? So here we have some k local Hamiltonian. Now instead of being these classical variables, it's over qubits, right? So the local dimension is d, and we have n quantum qubits. And the constraints now, before it was just this function, now we just choose any Hermitian matrix that we wish, right? So, but here the constraints were local. Here we also want the quantum constraints, these Hermitian terms, to be local. So they only act non-trivially on at most k qubits, each one of them. And as here we had this unsat, here we had something similar. But now we want to satisfy as many quantum constraints as possible, and this just means minimizing the energy of them, right? So we just want to find the minimum energy of this model, which is just the minimum eigenvalue of this matrix, right? So if you just think as a matrix, this is just some matrix is a sum of local matrices, right? So it's a very particular kind of sparse matrix, and we want to compute the minimum eigenvalue of this. Okay, so there is this connection between these two problems, but there is also interesting differences, right? So first, for the classical problem, if you want to find this optimal assignment of constraint satisfaction problem, this can be a computationally hard problem. I won't get into that. It's not the topic of this talk, but it can be NP hard. What's interesting is that if you want to find the optimal assignments of this quantum version, this seems to be even harder, right? So as we'll probably see in Daniel's talks in a few days, there is like a computational complexity way of saying that. It's a QMA hard problem. But what matters for this talk is that clearly there is a difference, right? Because if you look at the optimal assignment in the quantum case, it's just the eigenvector of minimum energy. Yeah, you have to behave. Yeah. And this can be a highly entangled state, right? So in the quantum case, the optimal assignment can be an arbitrary, at least if treated as a black box, could be any unit vector on this vector space, and this can be a lot of entanglements. So really what I want to address is to try to, in certain cases, to try to understand how entangled this ground state is and its properties. And I will do this today, tomorrow, consider two different situations. So what I want to consider today is to understand when we get a good approximation to, for example, the ground state energy, when we just neglect all the entanglements in the system, or most of it. So suppose I would just use some product states instead of a general entangled state as some approximation to the ground state. When does it work well? And first, there is a lot of work in this direction, starting from the 80s maybe, or even before, which connects these two definite theorems that Graham already told us this morning, and I will show you this. And then I want to get to the main topic of this lecture, which is a way of trying to understand this connection of definity and this product state approximation using tools from quantum information theory. And today in particular, we are going to use more the formalism of quantum information theory, just using definitions of entropy and many properties that we have from the entropies, which turn out to be useful in understanding correlations in these systems. So it'll be like entropies, chain rule, physical inequality, and so on. And I will get to that. I will show you what they are. Then tomorrow, I want to focus on a more particular class of things, like ground states in one dimension. And then I want to show you that we can get, some cases, good approximations to those, going beyond product states, but it's still controlling how much entanglement we have there. And again, I want to show you how information theory is useful for this problem. But then I want to consider the other half of information theory, which is really protocols, right? So using protocols from quantum information theory, like state merging and so on, to address this problem. Any questions? Okay, so the goal would be to approximate the ground state energy of the model, but the problem changes a lot depending on how well we want to approximate this ground energy, this minimum eigenvalue. So this is what we're interested, right? The minimum energy of Hamiltonian is just the minimum eigenvalue of this matrix. We might be interested in approximating this quantity up to some small additive constant, epsilon. So we want some small total error. That's one approximation scale. But what I want to consider today is when we are happy if you can approximate to some small extensive error, right? So this is a Hamiltonian, and it has like L interaction terms. So we expect the total energy, like the maximum eigenvalue of this, to be of order L. So we are happy if we can approximate this to some small constant epsilon times L, the total energy, right? So in other words, you can think as approximate the mean energy of the model. And this is the kind of approximation that I will show you here how to do it. Okay, so first this idea of just considering product states and seeing what you get, it's used a lot in physics. So sometimes it's called mean field, it's called other names too. And it's really just that, right? So we just, instead of to compute the minimum eigenvalue of this, we should optimize over all states. We just optimize over, or he should be minimum. We should, or put a minus sign. We just optimize over product states here instead. And we see what we get. We see if it's close enough to the true solution. And I'm just claiming this is a constraint satisfaction problem then. So why is that? Well, because this h of j, it only acts non-trivially on a few sites, right? So let j1 to jk be the sites where it acts non-trivially. If this is a k-local Hamiltonian, then there is at most k of them. So this term, we can write like that, and it only depends on the variables on j1 to jk. So it's really some function that only depends on a few of the variables. We can think of the entries of this psi as the variables, and therefore it's a sum of local constraints, and it's a constraint satisfaction problem. Okay, so first just this mapping, right? It's a mapping from quantum to classical, if you want to see like that. So this is used like in quantum chemistry. People use it a lot in condensed matter too, and they observe in many situations it works well. Not in all of them, but in many of them. There is some intuition why it should work well, and we're going to see this more later. So first, we expect that this will work well when there is a lot of interaction. So like each spin is interacting with a lot of other ones, and we see this. We can think of this as manifestation of monogamy of entanglements later. And also, if you don't have a lot of entanglement in the state, then you expect that if you just break the entanglement completely, you should do a good job, and you try to see how this emerges as well. Okay, so to start, let's see what happens if you have a Hamiltonian on the complete graph. And let's in particular try to connect to these definitive theorems that Graham told us this morning. So we have a Hamiltonian on the complete graph. So here's a complete graph. And the Hamiltonian is just, each particle interacts in the same way with all the others. So we can, just for convenience, let's define this H tilde, which is just the expectation of the graph, which is this complete graph of the local interaction term Hij. Right, so if you want to write as a sum, it's just that, right? 1 over n squared. We have n squared local terms, and the sum of all of them. And they are all identical, this Hij. Okay, so everyone interacts with everyone. Now, this has nice properties, it's Hamiltonian. In particular, it's permutation symmetric, right? So if you just change the order of the spins, nothing happens to the interaction. So if you want to formalize that, you can just define this operator, which is just a symmetrization operation. So P of pi, so pi is just some permutation on n elements, and this P of pi just change the order, right? So it's just a representation of this permutation on this n-fold vector space, and just change the order like this. And here we're just taking some matrix and symmetrizing it, right? So this is permutation symmetric for any x. And the Hamiltonian has this property that it stays the same if you symmetrize it. Okay, good. So now you see that feels like maybe some definitive theorem might be useful here to address this problem. And it turns out it is. And this we know for a long time. Oh, yes, no.
Have you got a factor of, you don't think you have a factor in your definition of the symmetrization there, of n factorial?
Oh, yeah, good. Thanks, of course. Yeah, sorry. Yeah, right. So it should be like 1 over n factorial and this sum here. Thank you. Any other question? Or remark? Or correction?
Shouldn't that n squared be n choose 2?
Yeah. Thank you. Any other?
Let me go back some of the slides.
I'll go back some slides, yeah. Okay, so I was going to raise that, and then Richard said that maybe it would be useful, and indeed it's useful. It's almost like some copy of what I have here, but then we can go fast maybe here, right? So let me just remind you a little bit of this history of definitive theorems, and just to show you that this connection with this, of trying to approximate this ground state energy and definitivity was done a long time ago. So first people in mathematical physics, they consider this infinite version of quantum definitive theorem, where you have a state which is infinitely extendable, right? Comes from a infinitely large symmetric state, if you want to think like that. And then this is a convex combination of product states. This is what Graham told us. And then, based on this work, already in 1989, Raju and Werner, they realized that this infinite definitive theorem should be able to tell us something about mean field and how it works, at least in the limit when n goes to infinity, for example. Then there has been this nice new proof that Graham also emphasized, this new proof by Case, Fuchs, and Sachs, from the infinite-definetic theorem, using kind of already some ideas from information theory, in particular using informationally complete measurements. And we're going to use similar things later on once I show you some new results on this definitive business. Then there was the first finite definitive theorem by Kanish and Renner, and this nice formulation, right, that we saw before, where if you have just symmetric state on n particles, you consider the k-reduced one, then this is close to a convex combination of product states, even ID states, up to this arrow. So local dimension square, k over n. And then we can just use this and see what we get for this approximation. Yes?
Maybe you talk about that later.
Yeah.
It seems from what you have presented so far that an essential assumption here for using the definitive theorem is that each part acts with each other part equally strongly.
Exactly. So at the moment, I'm just considering, yeah, they're all the same here. This is one of the things I'll try to relax later on.
Oh, you can?
Yeah.
Okay.
But just using, yeah, that's a good question. Just using this normal definitive theorem, we cannot relax that because we need this permutation invariance. But there is some ways of relaxing that, and this is what I will show you soon. Okay, so we can just try to apply this result, right? So let's see how we do it. It's pretty simple, and I think it's very nice. So we want to approximate, right? So remember, this H tilde already has this, there should be n choose 2 here, right? But already has this, this right approximation ratio. So what we would like to do here is just approximate this up to some small additive correction. This we can just write as, this is equal to the minimization over all states of trace rho H tilde, right? It's just the minimum eigenvalue. But because this is permutation symmetric, we can actually put the symmetrization here on rho. So we can just take rho to be a permutation symmetric state without losing anything. But this guy is just a sum of local terms, right? It's a sum of n choose 2 local terms. They are all the same. So we can just write this as H12, one of them, and the reduced state of this guy. Oh, here's a mistake. Sorry. Here should be, let me write, because I did something wrong. This should be this. So it should be rho tilde 1, 2, which is trace over 3 up to n of the symmetrization of rho. Okay? So there should be a symmetrization here before the partial trace. But then this is good, right? Because this guy, that one, is, we can just think as coming from, right, from a big symmetric state. And therefore we know that this guy is close to some convex combination of product states, right? So by definitive, right, we know that this term, it's always bigger if you take just the minimum over any sigma now on one copy of the space, and sigma tensor 2, right? This follows from this up to the arrow that definitive gives. So this has operator norm 1, right? Definitive is in one norm, so it all works nicely, right? And this is the approximation already, right? Because we know that if you just minimize over this smaller class of states, of course, this is always bigger than the minimum eigenvalue, but this just gives that it's also bigger than the same thing up to this arrow. Yes?
Actually, you lost me at the last equality from the first line.
Here?
Yeah, that's
Yeah, because it's wrong, right? It should be here. It should be.
No, with that.
Ah.
I think it's fine because you have the constraint that rho is symmetric.
Oh, right. Yeah. Yeah, indeed. Yes. Right. So here is the minimum over all rho, and then we can symmetrize it. This is the same thing as just the minimum over all rho, which is permutation symmetry. And then this guy, it's a sum of many local terms. So this guy, maybe I should write it. Yeah, right. So this guy, for example, the first term is H12, tensor identity on the rest. So you take the partial trace over all the other systems, and they're all the same, right? So they all give exactly this kind of term.
So you are at this moment assuming that all interactions are two-body.
Yes, I am. For this, it would work even they're not all two-body, but later I will need that anyway. So let's just keep to the simplest case. Any other question? Okay, right, so what this says is just a very nice argument. Definitive shows that this product states, or these mean fields, if you want, gives a pretty good approximation with this arrow, 2d squared over n. So the more particles you have, the better is this approximation. But as this only, right? So to apply this definitive theorem, we need this permutation invariant Hamiltonian. And it would be good to relax this if you can, right? So this is the first thing that I'll try to show you how to do it. And second, would be good if, so right, this means that maybe not all the terms has to be the same, but also maybe it would be good even if you take any graph you want, right? So let me show you the result, the main result I want to show you today, and then the rest of the time I'll just give you some ideas on how to get it. So the result is the following. Suppose you have a Hamiltonian, H, and it's too local, okay? So imagine like you have this interaction graph. Whenever you have an edge, you have interaction between the two sides. So it's too local because only it's a graph, right? Not a hypergraph. So the local dimensions, imagine, is d-dimensional. So this is the graph, set of vertices and edges. And we have this number of local terms, right? Just the number of edges in this graph, okay? So then the theorem says that you can choose any, like some grouping of these sites. So you just choose regions the way you want. So for example, choose these ones, where each one of them, x1, x2, and so on, is composed of m sites, okay? So we just doing some blocking on these variables. And then the result says that that you can get some estimate on how well the product states will work. So first, the product states will be big product states. So each one will be any state that you want inside the region x1, this is psi1, then psi2 any state here on region x2, and so on. Okay, so with like first, like almost like cross-graining the sites and then doing some infield there. And then it says, right, so this is the mean energy, right, the thing that we're usually interested here. So the total energy divided by the number of interaction terms. This says that this is smaller than the true mean energy, which is just the minimum eigenvalue divided by the number of interaction terms, plus some correction, which is some constant. Then d square is bad, it's like the local dimension. So when the local dimension grows, this becomes worse and worse. Now divided by the degree of the graph. So we are assuming that this is a regular graph. You can relax a little bit, but let's suppose it is now. So it's a regular graph, and the degree is there. So this is one thing. So the larger the degree, the better. And the second is this quantity here, which is the following. So this is the von Neumann entropy of the state on region xi. Okay, so we consider the reduced state on region xi. We take the von Neumann entropy there. It's a measure of entanglement between xi and the rest of the lattice. And we just take expectation over all regions, right? So this is expectation over the choice of xi. And this is the entropy in the ground state of xi. So we take the ground state, look at the reduced state. This might contain entanglement, so this might be non-zero. We take the average. And we just, right, so the maximum of this entropy is m times log t, because it consists of m d-dimensional quantum systems. And this just then, right, so this is always smaller than log t, and this is saying that if it's much smaller than 1, then you have a good approximation, right? So if you want to forget about d, it might be simpler, just in terms of qubits. This is always smaller than 1, and if it's much smaller than 1, it gives a good approximation. Yes. This is the minimum eigenvalue. So this is using the true ground state, right? And this is saying that the energy at, right? So of course the two states might be very far away, if in trace norm, for example, but it says that at least in terms of energy, if this term is small, it does a good job. Any questions? Okay. Right. So I just would like to explain, like, what it means, these two approximations.
Sorry, Fernando,
Yes.
to interrupt. So there should be some relation between m and n, because this becomes better and better as you consider larger n.
Oh yeah, but the price you pay, suppose that m equals n, right? Then this doesn't say anything, because of course you can just put any state you want on all the sides, right? So this is only interesting when m is very small.
Yeah.
In particular, if you want to get a state that you could write down on a classical computer in a reasonable time, this m should be at most log n, right? Order log n.
I think even m equals 1 is an interesting case to think about.
M equals 1, yeah, sure. Yeah. Well, when you have no grouping, right? It's also interesting. Yeah. Then you have something in terms of degree. Okay, so one of the motivations for looking at these kind of things, it's related to quantum complexity theory and some problem called quantum TCP. But I don't want to get into that. So if you want to know about it, just ask me later. So I will just skip this slide, because I want to go to the proof and show you how information theory appears there. So what I want to mention is just, right, so one thing that this result shows is this intuition that I mentioned before, that mean fields becomes better when you grow the coordination lattice, right, for example. So in one dimension, it's bad, there is not a lot of neighbors, then here more neighbors, and 3D more, and so on, right? And this just shows that you improve mean field better more and more when you increase the number of neighbors, right? Because you have this 1/degree factor. Another thing that it depends on is on this, right? This is like the average entanglement in the state, right? So, and again, you expect that when you don't have a lot of entanglement, maybe you can just break the entanglement completely, right? But I think it's interesting because it appears in a non-trivial way. So let me show you what I mean by that. What I mean is that if you can find some partition for which the entanglements in the ground state satisfy what we call subvolume law, right? So the maximum value of this would be of order n, suppose this is small o of m, right? So it's sublinear in M. Then this shows that this term goes to 0, and you have a very good approximation, right? So it shows that whenever you have a subvolume law for some partitions of when M is not too big, when the size of each one of them is not too big, actually you can break the entanglement completely, right? So there is one regime where this is pretty easy to achieve. It's when this expectation of the average entanglement is just some epsilon, something very small. Then I'll show you later what this is, but if you know by something very basic about entropy, p-square inequality, we can show that this guy will give approximation of order square root of epsilon, right? So this is the maximum value of entanglement, right? This is 0. Clearly, if it's 0, the average entanglement, then product state is exactly a ground state. This just says that when it's epsilon, then it's still pretty good, right? It gives this kind of error. But this result that we get is, I think, it's stronger because only if this is subvolume already, right? So if you're like here, epsilon log the m, then this already shows that you have error which goes like some polynomial in epsilon, right? So much before than when the entanglement is actually small, you already can break it completely, right? So it's some dichotomy. Either it's extremely large the entanglement, or it's not so large and you can just throw it away without getting too much error. Okay, any question? There is also cases where this fails, right? There's examples for which all these terms are bad. Or this is a term I gloss over, forget about this. I just forgot to remove. So imagine this model, a model where you have the sites, and the sites, each site consists of 3 qubits, okay? And each of the qubits of the sites connect to some other sites, and this graph is such that it's an expander graph of degree 3, okay? So because the expander graph, this is just the average expansion is big, this doesn't matter here, but what matters is the degree is small, so this doesn't give a good error. And because we just force the local terms to be such that you have an EPR pair between all these edges here, okay? Now, because the expander graph, doesn't matter how you choose these regions, there is a lot of edges going out, right? And each edge that goes out contributes to 1 bit of entanglement. So this just shows that this term will be pretty big too. It will be like a constant. So this is a kind of model for which we cannot say anything, okay? So let me get to the idea of the proof now. So the idea is all exploring this, that quantum correlations are non-shareable, right? So this monogamy of entanglements. So maybe Aaron will talk more about it. Maybe Thomas tomorrow, I don't know. But there are several ways of talking about monogamy. It appears in different contexts. And here we try to explore it to show when product states do a good job, right? So the intuition is very simple. Suppose you have a site here, and it has many neighbors. Then, because we're interested in this extensive error, if you just get right the energy with most of the neighbors, we are happy, right? But by monogamy of entanglement, this guy cannot be highly entangled with many of them, right? Maybe just with a few of them. So it means that if there is a lot of neighbors, it's fine that we just break the entanglements and look at this product state approximation. But and the entropy makes sense that it appears because the bigger the entropy here, then the more entanglement there is, right? So the more entanglement it can have with its neighbors. So when this is very small, it cannot be very much entangled with the rest of the world, and therefore we might want to explore that. To make sense of this, we use information theory, as I said. So the inspiration for this comes from work on constraint satisfaction problems, where they use classical information theory there, and there they're interested in algorithms, and they try to bound certain hierarchies of semi-definite programs, like sum of squares hierarchy, and they show it does a good job for particular problems. But the idea is this kind of same ideas we're going to use, which is talking about correlations between these variables and seeing how these correlations can be spread there and try to bound them. So to do that, we want to use like basics of information theory. Let me just remind you the quantities that we are going to consider. Are there questions so far? Okay. So one thing that we are going to consider is a measure of correlations between two random variables or two parts of a quantum state, right? So the mutual information. So one way to write the mutual information is just as some relative entropy of, for example, here for probability distribution on x and y versus the reduction on px and py. So the bigger this is, the more correlated x is with y. So one useful property of the mutual information is p-square inequality, or here should be bigger or equal. It's not equal. Okay, so the mutual information is always bigger or equal to this quantity, which is just the square of the trace distance between the probability distribution and the product ones, right? So this says that if the mutual information is 0, then actually the only way this happens is if there is no correlations, if the probability distribution is product. Another thing that we are going to consider is the conditional mutual information. One way to define it is the following: is just how much the mutual information increases when we put some extra random variable y, right? So is the knowledge of x about y given z. And one way to write is just this. It's the mutual information of x versus yz minus mutual information of x with z. Once we do this definition, then this property follows trivially, right? But it's very useful. It says that if you look at the correlations between x and y1 to yk, we can write this as a sum of n terms, k terms. One is the mutual information of x with y1, then the mutual information of x with y2 given y1, up to the mutual information of x with yk given y1 to yk minus 1. And also mutual information, there is a bound on how big it can be. It can be at most the minimum of the log of the alphabet of x and the log of alphabet of y. Okay. So now, if you just put these two properties together, so imagine, so this thing here is always smaller than log alphabet of x, right? And is equal to the sum. And therefore, there must be at least one term in the sum which is smaller than that guy over k, right? Which is the number of terms in the sum. Well, it should be k minus 1 here. So this is like some very simple result, but it will be useful, right? That if you take t plus 1 random variables, x, then there exists some t, k plus 1 random variables. There is some t for which the mutual information between x and yt, condition on y1 to yt minus 1, it's small, right? It's like log x, which maybe doesn't scale, divided by k, which might be something that scales. So this is one thing that we're going to consider. Okay, but this is about random variables, and we like to talk about quantum states, right? So luckily, quantum states, all that I said is true, right? So we just change probability distributions by quantum states. So that's great, but there's a problem, and the problem is what I didn't tell you about this quantity. The problem is that it's nice to condition on classical random variables, but it's not nice to condition on quantum states, on part of quantum states. We don't know how to make sense of this, right? So conditioning on quantum is problematic. So if you have 3 random variables, x, y, and z, another interpretation of the conditional mutual information is the following. So the conditional mutual information of x and y given z on this probability distribution P, you can think as the expectation over z, where z is taken from the reduced probability distribution P of z, of the mutual information of x and y on the conditional probability distribution on P of z. So this P of z is just the probability distribution of x and y given that we choose a particular z, right? So there is a nice way of thinking about this as some average mutual information over conditional probability distributions. And we know nothing like this for the quantum case. So even though chain rule is the same, quantum and classically, is not as useful because this conditional mutual information in the quantum case, it's difficult to make sense of it. And this is one thing that we have to overcome in the proof. But now let me show you how to put together these properties that I mentioned and that almost works, but doesn't quite work because of this problem with condition on quantum, right? So let's consider some easier problem. Suppose we don't have a quantum state, but we just have a probability distribution, okay? And later on, we see how we can change this by quantum state and what happens. So the idea is that we have our interaction graph, right? And now let's consider exactly this case when m equals 1 for simplicity in the beginning. So let me go back, show you. Right, so here we could do this grouping. Now I want to prove just for the case when m equals 1, okay? So then this is not interesting. What I want to get is just this 1 over degree dependence for the moment. Okay, so let's see how we can get that. So we have this graph, right? And then the idea is really to explore chain rule to our advantage, right? So as I said, chain rule implies this result that, right, so what was the result of chain rule? It was that a consequence of it is that if you choose k, then we can always find some t smaller than k for which the mutual information between zi, which is some random variable, and zjt, condition on zj1 up to jt minus 1, this is small. It's smaller than log d over k, right? This is the alphabet, should be sigma. So log alphabet over k. Okay, so this is true without this expectation, right? But because it's true, we can just take expectation. So we just take expectation uniformly at random over I, j1 to jt, right? So these are just positions on the graph. So we choose I at random, and we choose j1 up to jk at random. And using this chain rule, it gives us this statement, right? It tells us that the mutual information between zi and jt is small, right? It's small, but we have to condition on some other random variables. But now we can use this nice thing that we can see this as some average over mutual informations on a conditional probability distribution, right? So let's define this conditional probability distribution Q, and it depends on what we are conditioning on these random variables. So this is like, suppose we condition on z j1 being equals to z prime j1 up to z jt minus 1 being equal to z prime jt minus 1. And then this is a probability distribution on the remaining random variables that we don't condition on, which is just this, right? It's the conditional one. And then, well, by this property that I mentioned, we can write this in the following form, like that. So we take expectation over j1 to jt minus 1, these guys. Then we take expectation over the outcomes, right? Which are these outcomes. It's like what the possible values of these random variables here. And then we take expectation over I and jt, right? Because for those two positions, we don't condition on any outcome. And this guy then is just the mutual information of zi with zjt on this conditional distribution Q. And the results say that this is small, right? This is smaller than k. When k grows, this becomes smaller and smaller. So you see, this suggests what we should do, right? So maybe what we should do is we should choose some of the positions at random, t minus 1 of them, like this j is here. And we should just choose some sample from the distribution, choose some outcomes, which is this one. And then on average over these two things, what remains, the probability distribution that remains, is such that all the bipartite reduced probability distributions are close to products, right? Which is something in the right direction. So this is what we want to do, right? So a consequence of this is the following. Oh, sorry, before, any question here? I know there's a lot of indices, but if we have a question now, it's the time. Okay. So what this means, to sum up, is that if you condition on this j1 to jt, then on average, right, over the choice of them and over the choice of outcome, first, this introduce error, right, this extensive error, k over n, right, because we are messing up on at most k of the positions, and we have n of them. And this leaves a distribution, q, which satisfies this property, right? So that the expectation over pairs of the mutual information is small, right? Smaller than that. And this is just a constant because, right, so here we have in detail, here we have an expectation. We want to just say that we want to maybe use Markov inequalities, right? So on expectation is small, so it means that with high probability over the choice of these two guys, we have something that is small as well, losing a little bit. So this doesn't matter too much. But okay, but it's still not quite what we want, right? Because this is expectation over 2 random pairs. So like, this just says that this guy and this one, for example, on average, right, of the choice of them, they are close to product. But we don't care about this pair, right? Because there is no interaction term between them. We only care about the pairs which there is an edge connecting them, because then there is some local term in the Hamiltonian. But then we can just convert these two expectations, right? So this is expectation over all pairs. This is expectation over only pairs connected by the Hamiltonian. And we can connect them using this factor, right? N over degree of the graph. Right, for a complete graph, so the degree will be n, right? Because each one has like interacts with all of them, so this will be 1. If it's not complete, then we pay this price. Okay, any question? Okay, good. So now, okay, mutual information is a nice way to set correlations, but if you want to bound the energy, trace distance is more useful, right? But we have p-square inequality, so this directly implies that, right? So so this norm square is always smaller than this mutual information. Then we take expectations and x to the square is convex, so we get this relation. And now we just can choose k the way we want, right? K was this free variable. So let's choose k, right? Because we are paying 2 prices for k. One price in the energy is because in the end what we do is say, well, there is no correlations. Instead of this guy, we just have the product once. Then, well, this works fine, but we pay this price, right? Because it's not exactly true. But we also pay a price on the number of guys that we mess up, that we just measure completely and see what we get there. And this is the price we pay there. So we have to balance these terms, right? This goes with k, this goes with square root 1 over k. So if you just choose k equals epsilon n, a small fraction of the sites we are going to condition on them, we get this error, right? We get the error which goes like log d over degree here, epsilon plus epsilon. And we just choose epsilon to balance these two. So in the end, we have like 1 over degree to the power of 4, right? 1 over 4. Okay, so the idea here is, maybe it's too much detail. You shouldn't worry, but that is really simple. It's just that because of chain rule, given a probability distribution and later receiving a quantum state, if you just condition on the values of some of the positions, where we choose at random them, then most of the pairs will be close to product now. Right, so it's one way to decouple quantum or probability distributions of quantum systems, but without having to use symmetry or anything like this.
Is it right to consider epsilon as a small parameter? Because then I'm
Yes.
about it sitting in the denominator.
Yeah, but that's why in the end we choose this epsilon to be like square root of c log t. No, sorry, to be. Let me write it. Maybe. So choose epsilon to be c log t degree 1 over 4. Right, then you balance the terms and you get 2 times that as the final error. Okay. Okay, good. So, but why this doesn't really work, right? Doesn't really work because we're really exploring this property, right? That this guy we can see as expectation over mutual information of a conditional probability distribution. If you just want to apply the same thing directly to quantum states, we lose that. But luckily, right, the answer comes from the same way that this definitive theorem was proven, right? Which is using this nice mapping between quantum states and probability distribution, which an informationally complete measurement gives, right? So we just want to use an informationally complete measurement here. So there are many constructions. Let me use the following one from this paper. So it shows that there exists some P of M. Here I just write as a quantum classical channel, but this MK just form a P of M, right? So maps a quantum state to this probability distribution. And it has the property that for all K and all 2 states, rho and sigma, on K copies of the vector space, then if you look at the variation distance of the probability distribution of the post-selected, of the post-measurement states, right? So these 2. First, of course, this is always smaller than the trace distance of the states, right? But actually, in this case, it's bigger than the trace distance of the states times some factor, which is pretty bad if k is very big, right? So decreases exponentially with k and some polynomial in t. But ultimately, it will be interesting when k is like 2, because we are talking about 2 local Hamiltonians. So this will just be a factor of local dimension. And so this is how we want to proceed. We just want to use these informationally complete measurements to get a problem about probability distributions, which then I show you there's a way of handling it, and then mapping back to the quantum states by using this nice property of the informationally complete measurements. Any questions? Okay. So just some proof overviews, just some words, then I show you a little bit more detail. So how we want to ultimately do it? So what we want to do is we measure epsilon n qubits. We choose them at random, and we measure them with these informationally complete measurements. Okay, and then we just condition on outcomes, right? So just condition on possible outcome, and then with high probability over this choice of outcome, this will change the energy of the state, of course, because we are measuring it, but it will only change by error at most epsilon, right? If instead of just conditioning, we would just measure and forget about the outcome, then we're just messing up with epsilon n qubits, and therefore the error is epsilon, right? But by Markov inequality, if we condition on outcome with high probability, the error will be some constant times epsilon, right? Maybe it should be some c times epsilon. Doesn't matter here too much. Then okay, once we condition on the sites, then the intuition and what I showed you before classically, and it will be true quantum as well, is that most pair of qubits that we didn't measure, they will have small mutual information. And how small will be something like this, right? Log d over epsilon degree of the graph. But this is really just but this is really just the mutual information of the probability distribution associated to them, right? So you just think as we have the quantum state on them, you apply this informationally complete measurement, and then you look at the mutual information. And then this will be small like that, right? Because this is the argument I showed you before, the classical argument. But this is a mutual information run on variables that comes from measuring a quantum state with a informationally complete measurement, right? So we can convert back to the mutual information of quantum states, and we lose a factor which is like polynomial in D. And then, then the witness, right? The approximation of the ground state is just this product state, right? And the total error is something like this in the end. So I'll show you this now, don't worry. And then we choose epsilon to balance the terms. And if you want to get entanglement, you just cost grain first the sites and then apply something similar. So the idea is really just we can think about classical random variables as long as we first apply this informationally complete measurement and pay the price back to convert it to quantum states, right? So if you want to see some formula, so this is the ground state, and we measure all the sites with this informationally complete measurement. Then we get the probability distribution of the possible outcomes, right? So this is something that we want, right? So it's like this is the average like entanglement. This xi, let's assume that it's just one site because it's simple. If you want to cost granite, there's some other problems, but I don't want to mention them, right? So this is just one site. Is the average entanglement of the sites. But because it's a pure state, actually we can write this as the mutual information, right? So twice the entropy is equal just to the mutual information of xi with all the other sites. So this means all the other sites, not I. Okay? This is just some equality that we know. But we can now start to trace out some of these sites, right, in the quantum states. And mutual information is monotonic, right? It's like data processing inequality. So we have that this is always smaller than the mutual information of xi with a few of the j's which were here before, right? We just choose j1 to jk positions at random, which are different from I, and we look at this mutual information. So it can only go down, right? Because there were more positions here before. And here now we just measure. So this is the quantum state, psi 0. We measure all sites with informationally complete measurement. But again, this can only decrease the mutual information, right? So now we have a mutual information over the outcomes of this informationally complete measurement. And again, expectations as before. But this is the thing we started with, right, in the classical case. So this is something that we know how to handle. So if you just follow the previous argument, what we can show is that for these random variables, we have this kind of statement, right? On average, over the remaining sites that we don't condition on, they will be close to product up to this error. And this Q is the probability distribution obtained by conditioning on these T sites that we chose to condition on, right? But now it's not really a problem anymore because we have this informationally complete problem measurement, right? So we can bound this norm. We can bound the norm of the true quantum state. So this sigma is the state we obtain by measuring this measurement on J1, Jt in condition on outcome. we know that this guy, we can upper bound it by the measurement one, right? This is the measurement ones over m up to a factor of t. We lose a factor of t. So from this bound, we get this one. And then, well, then we can do as before, right? So we mess up a few of the sites, like k over n. So we choose k as before, and we get this kind of error, okay? And that's it. So sorry, maybe it's too much detail for after lunch, but I think what I wanted to convey is just that, right? That we have a problem on classical probability distributions, and that chain rule leads to this decoupling between these classical random variables, and that this actually implies something about quantum states, because we can first apply informationally complete measurement, and then work out the classical thing, and then go back to the quantum, paying a price that only depends on the local dimension, right? Because here we only have to invert the problem on two sides, right? That's why it works here. Any question? Okay, so let me just mention some other applications without much detail. So this is really about the existence of a good product state approximation, right? But doesn't tell you how to find it, for example. And as I mentioned, to find it even for classical problems can be a NP-hard problem. So we don't have a hope of finding it in general, right? But in some particular cases, we can find using extending some classical results. So following the same approach, exactly this mutual information business and so on, we can actually obtain polynomial time algorithms for some kind of problems, okay? So 3 examples are like planar Hamiltonians. So the interaction graph is planar. Then there was work in this direction before by Brandao, Bravi, and Terral, but they had a restriction on the maximum degree they could tolerate, and we can get rid of this restriction just by, just by showing that when you have a vertex with a lot of neighbors, actually we can just replace by something product and they state on the rest. And by monogamy, this gives a good approximation. For dense Hamiltonians, also you can get an algorithm, and this improves on previous works by, well, it was an open question by Garib and Kempe. And something that I won't mention, but I think is interesting, also Hamiltonians on graph with low threshold rank. So this is just a graph for which the number of very high eigenvalues is bounded. We don't have a lot of eigenvalues. So like some generalization of expanded graphs. Then this works as well. And there was classical work in this direction, we generalize it. And this we use something that I think Aaron mentioned, Lasser or sum of square hierarchy, and we get some version in the quantum case. And I want to mention that just because it is the same strategy as before, right? So we just show that product state, they do a good job in all these cases because of this like monogamy of entanglement argument. And in each one of these cases, we had good classical algorithms. So we can just use these classical algorithms because now we have a mapping between quantum and classical constraint satisfaction problems. So to finish my last slides, I want to go back to definitive theorems, right? That Graham was telling us. So if you pay attention, I guess you could see that maybe what was going on was a definitive theorem, right? What we were proving, without making it explicit, and that's true. But we can just make it explicit and see what we get, right? And see how it compares from before. And I think it's interesting because, well, on one hand, it's weaker in respect to some aspects. I will show you. But on the other hand, I think it's more interesting, or it's more useful in some applications because we need less assumptions. So this is a classical result. There is also a quantum version, but the classical is already new. It's really, you can see as a definitive theorem without any symmetry assumption, right? So definitive theorem is usually about a permutation symmetric probability distribution, and you look at the reduced one and see it's close to convex combinations of ID. Here, it's something that works for any probability distribution. So it looks very ugly, but let me try to explain what it says. So suppose you have a probability distribution on n variables, okay, over alpha, beta, sigma. And then what it says is that, and let's define this Q z prime of zi1 up to zik as the conditional probability distribution on zi1 to zik, condition on zj1 being equal to some z prime j1 up to zjt being equal to some z prime jt, right? So again, as we did before, we are just looking at the conditional probability distribution if you just, right, choose some of the values for these variables.
Sorry, how's K and T related there in that last explanation?
So T will be the number of variables that we condition on.
Yeah,
And K will be the number of variables that we look at. Right? So what the theorem says is that if you look at this guy, this conditional distribution, then it's close to product. Okay, so it's close to product, not convex combination of product, but just product. If we choose the j's that we condition on at random, if we choose the variables the values that we condition on at random, and if we choose the other guys that we look at, this k block, this k random variables at random, right? And it goes, the arrow goes like log alphabet and k square over t. Right? So if t is much bigger than k squared, then it works well. So this really is some kind of decoupling again, right? So condition of some of the variables, all the other blocks of size k, they're close to product. But we didn't have to assume, right, anything about the probability distribution, right? It's just somehow the randomness is coming that we had from permutation invariance there is coming from the choice of the positions here. And this is, well, this is, I think, what was behind the other proof, although they would go more directly to get Barry scaling. But so first, one thing that's interesting is that for classical definitive theorems, you have something that depends on the alphabet, and here you have log alphabet. But we also have a version there which is independent of the alphabet, and which then goes like k squared over t. So we have something very close to this, to the bound from classical definitive, with less assumptions. But we are worse because we pay this factor of log alphabet. Whereas with k squared over t, they have something independent of the alphabet. So again, we can get some quantum versions of this using informationally complete measurements, right, along the lines of these guys. But here is much simpler because the inversion the Graham told us it was difficult in that case is very easy here, right? It's trivial. We can also do something for like not for going to trace norm in the quantum case, but for some locality constraint norms, and maybe Aaron will mention this in his talk. And because we have this flexibility, we can now even go like to other sources of randomness, right? Not to uniform randomness here, but maybe like to Santa Vazirani source, which did recently and lead to some applications in cryptography. So I think this, this information theory view on these definitive theorems gives us a lot of flexibility that we can explore for different things, and I think that was the main point I want to get to you. So thank you for your attention.
Thank you. So, any more questions, comments? Go on.
One considers the discrete Laplacian acting on a graph, then one has an inequality for the lowest eigenvalue, which is related to the topology of the graph, expressed in terms of Cheeker's constant. Do you see any similar role being played in the inequality that you have in reflecting the topology of the graph?
So, yeah, a little bit. So let me. So because this is the bound that we have, right? So but maybe it's not in the more interesting direction. But suppose we have a graph which is expanded graph, right, and has very good expansion. Then the only thing that this can be true, right, when the expansion goes close to the maximum value, like half, then the degree has to grow as well, right? That's the only way to have a very good expander. And then this approximation gets better and better. So this shows that, the more expanding the graph is, the better is the approximation. So there's a connection like that. So what I didn't mention is also when the expansion is very bad, I remove from here because it's more expected. Suppose that all these regions doesn't expand too much, then again, product states they do a good approximation because they can just break all the interactions. So we have the two extremes: very expanding graphs, this works well; very non-expanding graphs, it works well; and in the middle, we don't know.
You mentioned a few slides later on about approximations of various costs of Hamiltonians.
Oh yeah.
By product states.
Mm-hmm.
Yeah, that's it. So are these okay? So here you have polytime algorithms. So you're not just approximating this by something in NP. So
yeah.
So what's the sort of approximation sort of scale you get?
Oh, it's the same. So we didn't even consider this very carefully, but what we know is that so for any epsilon that you want to compute, let me write. So given epsilon, which is a fixed thing, then to compute the ground state energy over the mean gross state energy plus epsilon plus minus epsilon, then this can be done in polynomial time in n. But the dependence on epsilon of the algorithm will be exponential, I think. So it will be like a polynomial time approximation scheme, right? Maybe something like n to the poly 1 over epsilon. But we didn't actually consider this very carefully, dependence on epsilon. We should probably. Yeah.
Is it known that you can't get like poly 1 over epsilon?
I don't know, do you know?
Yeah, if you do poly 1 over epsilon, then you can just take epsilon to be like, 1 over n to the 10th.
Oh yeah.
And then the factor to dense Hamiltonian would become a meaningless constraint.
Right.
So something like that is going to be necessary.
Yeah.
Any further questions? So thank Fernando again.
Thank you.